Okay, the last speaker of our session is Diana, who will tell us about high-dimensional subdiagram matching. Thank you.
Hey, good afternoon. Can anybody hear me well? No? Oh.
It seems to be on.
Okay.
Microphone working?
Like this? Is it better? Okay, thank you. Okay, so in this talk I will present my joint work with Amar Haji Hasanovic on the problem of higher dimensional subdiagram matching in the setting of diagrammatic sets, which is a model of higher dimensional diagram rewriting introduced by my co-author. So higher dimensional diagram rewriting is used in the formalization of higher category theory, higher algebra, homotopy theory, or combinatorial topology, but it is also endowed with a notion of computation via diagram rewriting. And by this, I mean that computations on n-dimensional data are themselves data of dimension n+1. So we are interested in seeing higher dimensional diagram rewriting as a model of computation, and we want to study the computational aspects of higher rewriting. And our goal for this work was to relate the derivational complexity of a higher dimensional rewrite system to the worst case time complexity of an implementation of a machine that operates via higher dimensional diagram rewriting. Okay, now, in this setting of diagrammatic sets, we encode the shape of a diagram by what we call an oriented graded poset, and I will explain what this means now. So, on the left-hand side, we have an example of the shape of a two-dimensional diagram in its pasting diagram representation, in which the zero-dimensional elements are the points, the one-dimensional elements are the arrows, and then the two-dimensional elements are oriented surfaces. And on the right-hand side, we have the Hasse diagram representation of the poset that encodes this shape of a diagram, okay? Now, an edge in this Hasse diagram representation records if an n-dimensional element is in the boundary of an n+1 dimensional element. So let's take an example. And I will use this element, this two-dimensional element that I denoted with 2, 0. And you can see that it has 3 one-dimensional elements in its boundary, 1, 0, 1, 1, and 1, 3. And there is an edge between 2, 0 to each of these one-dimensional elements in our Hasse diagram representation. Okay, now by graded, we mean that each element has a unique dimension given by its height in the Hasse diagram representation. So for example, the zero-dimensional elements are on the bottom level, the one-dimensional elements are on the next level, and so on. And then by oriented, we mean that we can give an orientation to the edges of the Hasse diagram to encode if an n-dimensional element is in the input boundary of an n+1 dimensional element, and this is encoded with an arrow pointing upwards or in pink, or if it's in the output boundary, and this is recorded with an arrow pointing downwards or in blue. And again, if we take this element 2, 0 as an example, you can see that it has 2 one-dimensional elements in its input boundary. So we have arrows pointing upwards from 1, 0 and 1, 1 to 2, 0. And then it has one-dimensional element in its output boundary. So there is an arrow pointing downwards from 2, 0 to 1, 3. And then I just want to mention that the color encoding here, it's redundant, but we just use it because it helps with the visualization. Okay, so now we mostly work with closed subsets of an oriented graded poset, and by closed I mean the downwards closure. And we can now give combinatorial definitions for the input and output n-dimensional boundaries of a closed subset of an oriented graded poset, which we denote with partial n alpha u. So we can then define the category of oriented graded posets in which objects are oriented graded posets, and then a morphism from P to Q is a function of their underlying sets, satisfying for all n and alpha this equation, so which means that the boundaries are preserved. And then we say that an n-dimensional closed subset is round if for all k less than n, the intersection of the k-dimensional output boundary of U with the k-dimensional input boundary of U equals the k-1 dimensional boundary of this subset. And I placed two examples here. So on the left-hand side, we have an example of a round closed subset, and on the right-hand side, we have an example of a closed subset that is not round. And intuitively, being round means that a diagram, we say that the diagram is round if its shape can be interpreted as a topological and ball. Okay, so now, not all oriented graded posets represent well-formed shapes of diagrams, and we only work with an inductively defined subclass of them, which we call regular molecules, and which are defined using the following three rules. The first rule is point, which says that the terminal oriented graded poset in the category defined previously is a regular molecule. Then the next rule is atom, which lets us go one dimension higher, and it works in the following way. So given two regular molecules, U and V, such that they are both round, they have equal dimension, let's say n, and their boundaries are isomorphic. We glue them along this boundary, and then we add a top dimensional, an n plus one dimensional element, and we obtain a regular molecule whose input in this case is U and output is V. Okay, and then the paste rule just lets us construct new regular molecule by pasting along their k-dimensional boundaries. So this works in the following way. So we get two regular molecules, U and V, and a natural number k, which is smaller than the minimum of the dimensions of U and V. And then if the output k boundary of U is isomorphic to the input k boundary of V, then gluing these two regular molecules along their k-dimensional boundary is a regular molecule. So I will now continue by giving you some examples of the atom and paste rule, and then I will go and talk about the higher dimensional subdiagram matching problem. Okay, so for the atom rule, I wanted to consider these two regular molecules. They are one-dimensional, so they have the same dimension. They are round, and also their both input and output boundaries are zero-dimensional, so they are isomorphic. Okay, so what we do next? We glue them along these isomorphic boundaries, and we obtain some kind of a shell. And then we add a top-dimensional element, in this case, a two-dimensional element, going from U to V, and we obtain a regular molecule whose input in this case is U, and output is what used to be V, like it's V. Okay. Now, for the paste rule, I will take these two regular molecules, and we need a natural number k that is less than the minimum of their dimension. So we have two possibilities. We have k equals 1 and k equals 0, okay? And I will start with k equals 1. And I highlighted here in purple the boundaries that are isomorphic. So the output boundary of U is isomorphic to the input one boundary of V, but the other way around, it's not true. So the output boundary of V is not isomorphic to the input boundary of U. And this is the only boundary along which we can glue U and V, and we obtain the following regular molecule. And then for k equals 0, we have two cases, because we have that the output boundary of U is isomorphic to the input boundary of V, but also the output boundary of V is isomorphic to the input boundary of U. So then we can glue them along this green isomorphism or along this orange isomorphism. We can obtain two different regular molecules in this case. Okay, now I just want to say that pasting of regular molecules follows all the equations of globular pasting in n categories up to unique isomorphism, and this includes the interchange law. Okay, and a consequence of this is that the pasting decompositions of a regular molecule are not non-unique. So if we take this regular molecule on the left-hand side here, you see that we have three possible pasting decompositions, one along the zero-dimensional boundary, and two which are pastings along the one-dimensional boundaries, and each of them is isomorphic to this regular molecule on the left-hand side. Okay, so now I told you what the shape of a diagram is, but a diagram in our setting is a labeling of a regular molecule into a set of variables. So what we do is that we are giving names to the elements of a regular molecule. So again, as an example, if we take this regular molecule on the left-hand side with the labeling below, then we obtain a diagram in the two categories of categories, functors and natural transformations, in which C is a category, T is an endofunctor, and in this case, mu is the monad multiplication. And then we call a cell a diagram whose shape has one maximal element, so a diagram whose shape is an atom. And this represents a basic rewrite in our system. Okay, so I said that we are interested in the computational aspects of higher rewriting. And last year, we studied the algorithms and data structures for constructing regular molecules. And one of our most important results was the traversal algorithm for solving the isomorphism problem for regular molecules, which runs in time O n squared log n, where n in this case is the size of the Hasse diagram representation, including both vertices and edges. And I just want to point that this runtime analysis is a bit better than the one we presented last year. So you can find all these data structures and algorithms together with some examples and documentations already implemented in our tool Revolt, okay, at the following address. Okay. So after this, our next question became, is a machine that operates via higher dimensional rewriting a reasonable machine by the standards of computational complexity? And to answer this question, I first need to tell you how such an abstract diagrammatic machine works. This machine has a list of n+1 dimensional rewrites whose input and output are n-dimensional diagrams, okay? And now, given an n-dimensional diagram T as input, the machine tries to match one of the input boundaries of a rewrite rule to a rewritable subdiagram of T. And by rewritable subdiagram here, I mean a portion of T that can be substituted and still produces a well-formed diagram. And once it finds such a match, if it finds such a match, then it replaces it with the output of the rewrite rule. So then the question became, is the obvious cost model that attributes constant cost to each rewrite step a reasonable cost model? And the answer to this question depends on the computational complexity of the higher dimensional subdiagram matching problem, whose answer is not at all obvious, since the problem of subgraph matching is known to be an NP-complete. So this higher dimensional subdiagram matching problem is the following search problem. Given two diagrams, S of shape V and T of shape U, such that the dimension of V equals the dimension of U and V is round, find, if any, all the inclusions of V into U such that the inclusion of V into U is a submolecule inclusion, which means that this inclusion appears as a factor in a pasting decomposition of U, and then the labels of the diagrams match. And this problem can be split into the following three subproblems. The molecule matching problem, which says find, if any, the inclusions of V into U. Then the rewritable submolecule problem, which decides if an inclusion is a submolecule inclusion. And finally, checking that the labeling is preserved. Now, problem 1 admits an algorithm that has a low degree polynomial time bound in the sizes of U and V. Problem 3 is easy and should take linear time in the size of the diagram. But problem 2, however, problem 3 is trivial, sorry. And problem 2, however, turns out to be more difficult. And I will shortly tell you why this is the case. So the molecule matching problem, this is the first problem, can be solved by making this UN number of calls to the isomorphism algorithm, where UN is the set of n-dimensional elements of U. And why this is the case is because our shapes of diagram are very rigid. So once we find a match of a top dimensional element in V with a top dimensional element in U, there is at most one way to extend this match to the whole of V. Now for the second problem, we have an algorithm for deciding if an inclusion is a rewritable submolecule inclusion in an arbitrary dimension n. But in this general case, the algorithm has a factorial worst case upper bound. However, we have class of diagrams. So if the diagrams satisfy a condition that we call stably frame acyclicity, then the problem of deciding if an inclusion is a subdiagram inclusion can be solved in linear time in the size of its Hasse diagram representation. Again, when I say Hasse diagram representation, I mean it includes both the vertices and edges of the Hasse diagram. And finally, we get that every diagram of dimension less than or equal to 3 is stably frame acyclic. So the problem of higher dimensional diagram subdiagram matching is feasible up to and including dimension 3. Okay, now I will tell you a bit. How this algorithm works on a high level, and then I will continue by giving some more details for the rewritable submolecule problem. So why this situation appears is because pasting decompositions are highly non-unique, as you've seen at the beginning of the presentation. So our goal for this problem is to find if V is a factor in a pasting decomposition of U. But again, as you've seen previously, there are many possible decompositions. So what we want is that we want to constrain the space of possible decompositions. And to do so, we parameterize it by topological sorts of a directed acyclic graph that has at most un number of vertices. And then the algorithm goes through all these topological sorts until it finds one that satisfies our criteria or it fails. So in the case in which the graph is discrete, we have a factorial number of topological sorts. Now for the stably frame acyclic regular molecules, we have the case that either all topological sorts work or none of them do. Okay, so it suffices to check only one topological sort. So I will now want to give you more details, and to do this I need to tell you more about layerings and orderings. So I will define this max U, this set max U, to be the subset that contains the maximal elements in U. And by maximal element, I mean an element that is not covered by any other element. And then for k greater or equal than -1, we consider the following set, which is the set of maximal elements with dimension greater than k. And the k layering of U is a sequence of submolecules of U such that U is isomorphic to the pasting of these submolecules in this order. And then the dimension of each submolecule is greater than k and contains exactly one element from this set mentioned above. So let me give you an example. Again, I will give you this example. So for this regular molecule on the left-hand side, it has exactly two maximal elements, which are two-dimensional, and then it has three possible layerings. So it has 1, 0 layering, and then 2, 1 layerings. And you can see that each submolecule in the layerings contain one maximal element. Okay, so one of these two cells. So now with this data, we can reduce the rewritable submolecule problem to the problem of finding an n-1 layering of U in which the maximal elements in the image of V are consecutive, plus checking some extra conditions. Okay, now how about the graph that I was talking about? So we define the maximal k-flow graph of an n-dimensional regular molecule U as follows. So the vertex set is the set of maximal elements of U whose dimension is greater than k. And then we get an edge from x to y if and only if the intersection of the top dimensional elements of the output k boundary of x and the top dimensional elements of the input k boundary of y is not empty. And finally, we say that the k ordering of U is a topological sort of this graph. And we have a relation between k orderings and k layerings, namely there is an injection from the set of k layerings to the set of k orderings of a regular molecule U. And by this I mean that a k layering uniquely determines a k ordering, but the converse is not true in general. So now we can give a more detailed description of the algorithm, and it follows the following steps roughly. So we first compute the n-1 flow graph of U, we then find the topological sort of this graph in which the vertices in V are consecutive. So this means that we find an n-1 ordering in which the vertices in V are consecutive. And then we check if this ordering is induced by an n-1 layering and it satisfies the extra conditions. And if this is not the case, then we iterate again to step 2 and we try to find another topological sort. So each of these steps can be efficiently computed, but the problem is that we may have to iterate through a factorial number of topological sorts. Now, a consequence of an n-dimensional regular molecule being frame acyclic is that for all k less than n, the k layerings are in bijection with the k orderings. Okay, so there is a one-to-one correspondence between k layerings and k orderings. And we say that a regular molecule U is stably frame acyclic if for all submolecules of U, every substitution in V produces a frame acyclic regular molecule. And then for these stably frame acyclic regular molecules, we have the case that either all n-1 layerings, such that the vertices in V are consecutive, satisfy the extra conditions, or none of them do. So just to make a little summary, so we have that the k layerings and k orderings are in bijection, okay? And then for the stably frame acyclic ones, we have that once we find an n-1 ordering in which these elements of V are consecutive, then we only need to check for that ordering. Like if it fails, then it fails for any such ordering or layering. Okay, so now the first example of a regular molecule that is not stably frame acyclic appears in dimension 4. And what we plan to do in the future is to study these examples, and we hope that a better understanding of their behaviors will either lead to an improved polynomial time algorithm for subdiagram matching in dimension 4, or to a proof of NP completeness. And well, in case we get a proof of NP completeness, this is very interesting because it will hint to a potential gap in complexity between the 3-dimensional and the 4-dimensional cases. Okay, thank you. There are any questions?
Okay, we have time for questions.
Thank you for the talk. So the complexity at higher dimensions is very bad, factorial and such. But have you, in general, I mean, but have you tried as a matter of practical solution to experiment with memorizations techniques for that? I don't know if the shapes that you usually want to solve and simplify are recurrent, but in that case you could basically store them in a table so that you don't have to recompute them.
So you mean like the shapes that we mostly use?
Yeah, so memoization basically means that once you solve a computational problem, you put it on the side in storage. And then every time you find a shape, before solving it, you look in storage if you already have that solution figured out. And if you do, you just copy paste it in. So in this way, if you have something that you know you are going to need to compute a lot of times, you save it and the algorithm can skip that part. So if your shapes are made of very recurrent kind of things that show up a lot, that could help.
Well, okay, yeah, this is a very good question. So at the moment, we did not implement these algorithms that I presented. So no, we haven't tried this. But the thing is that, yeah, our shapes of diagrams, they are very rigid, but also we have a lot of them. So the behavior, it's not very predictable, I would say.
Okay.
But the thing is that with the molecule matching algorithm, so this is this one, we do make the runtime analysis by considering the rewrites in V. So by considering the n+1 dimensional rewrites, we consider them as a constant time, like as an overhead, because this is something that you will always do. Like you have them there in your list of rewrites, so then you only need to consider the new diagrams that you feed into the machine.
Okay.
Used about one of the points that you made. So you said if you match, at some point you said that if you match a top dimensional face,
Yep.
then you can extend uniquely. But if I have like a graph with a central node and many edges coming off and I match one of those edges, how do I know where to send the rest of them?
Yeah, well, so the trick is that, well, let me go there. Where is this? Yeah, so, okay, the trick is that once we match one of the faces, we also match the boundaries. So we match the whole boundaries, like from n minus 1 until 0. And then, because the shapes are rigid, there is only like, so you can see that, okay, it's a bit hard to not draw. So you can imagine this like some shapes glued around some, glued at some boundaries. So then you match one of these shapes, so you match one of the top dimensional element, and then it shares an n-1 dimensional boundary in common with at most one other top dimensional element. So once you fix these boundaries, there is only one way to go to other n dimensional elements. So that's why we have that case. Yeah, and if that's like, if this fails at any point, then you need to try to match other.
I can't even build a graph that looks like.
Can you?
Something like that. Like a central node and then three.
This is not a, yeah, this is not a regular molecule. I mean, like a kind of a span or a cospan. Okay, no, this is not a regular molecule. Yeah, thank you for your question. It was a very good question.
Okay. Any further questions? Yes.
So you're talking about building a hypothetical machine that its model of computation was this higher dimensional rewriting. Would you implement that machine in current physical hardware, or is there like an idea of what a higher dimensional rewrite system physical hardware would look like?
No, unfortunately, we don't have any. I mean, we don't have an idea on implementing this on a like visible hardware system. At the moment, it's just theoretical and high level. And I think before reaching that point, we still need to solve these complexity problems. And yeah, and maybe comparing it with other existing models of computation. Thank you. Thank you for the question.
Okay, I think we might stop there for lunch. So let's thank our speaker again.